Okay, so I'll tell you about an equational modeling of asynchronous concurrency that I eventually come up while I was trying to understand what asynchronous concurrency was to be used. And the equational modeling is fairly simple, while the comments you can have on the internet about asynchronous concurrency, this goes in many directions. It's not easy at all. So the research context is that I am interested for some time by trying to define programming languages for the arts. So giving programming language to artists so that they have Turing complete power on the machine instead of using a paid application where they can only do what the application is proposing. So this is a very long-term thing. Anyway, doing so, I eventually realized that modern type functional programming languages such as Haskell, where you specify things as equation, this is rather quite a handy API for artists. I may check with artists. This is not that clear, but at IRCAM in Paris, they eventually convinced artists to program in Lisp, so there is some possibilities. We made some prototypes these last years, one for music, one for 3D animation, even eventually run on GPU. Since then, I forgot how to program shaders on GPU. And also recently at this year farm, how to do real-time audio processing and control under Haskell. Doing so, we eventually realized that monads, and especially the notion of monad streams I will detail, provide both handy API and efficient programs to do this. And also, maybe in art, there was a need of concurrency and parallelism. So concurrency to handle, for instance, with audio, audio streaming, which are rather synchronous streaming, and control streaming, which are rather asynchronous. They come when they come. And also playing, for instance, to melodies at the same time. This is some kind of simple parallelism. So the question was how to lift asynchronous concurrency that's available in, say, the IO monad to monad stream, and eventually to understand what is actually asynchronous concurrency over an arbitrary monad. So to make it simple, what is asynchronous concurrency? It's the possibility to asynchronously launch a computation and instantaneously get back the promise of a value that will be available later when that computation will be finished. As a matter of fact, I'm very surprised talking with two people during ICFP or ER that asynchronous concurrency is very popular among programmers. One of the reasons is that it's a very safe concurrency. It induces no deadlock. Well, as soon as you are doing real concurrency and say, for instance, process calculus, then you are defining two components and they are very nice, they have plenty of property, then you run them in parallel and your system breaks down because there are plenty of deadlocks. So in practice, this is very useful and it offers smooth control, so you don't need to wait unnecessarily. And it's available in most programming language. The less good aspect of asynchronous concurrency is that it's not necessarily very well understood. So first, there are plenty of API for asynchronous concurrency, and the notion of promises is not necessarily that well defined. I know no equational properties defining what a promise is. There might be some, but I don't know them. And also, as soon as you have a bit of asynchronous property, then concurrency, then you have plenty of additional utilities function. Should they be used? Are they safe, etc.? Nobody, I don't know. So, for instance, if you consider the promises as something acting over type, so a type function, does it form a monad? And the answer is quite puzzlingly yes in OCaml and no in Haskell. And in other languages, it depends. I think I read somewhere that it's definitely a monad in JavaScript. So our objective is to define asynchronous concurrency as a generic monad extension of a monad. to express the semantic of the basic asynchronous primitive I need by means of equational law, to analyze the properties of the resulting model, aiming at giving a programming language to artists. I have the deep feeling that the cleaner my programming language will be, in the sense that the stronger the underlying mathematical model will be, perhaps there will be an entrance ticket to pay to understand the model. But as soon as you achieve that understanding, then it's worth it, because you do have a really nicely defined model, and not something ad hoc. Okay, and eventually consider how it should be extended with nice additional primitives, and make some experiment. So in some sense, R programming can be achieved by monad, asynchronous programming, time and monad stream. Just meditate for 30 seconds. Why should we need equation? One reason is that we may have nice model. So, of course, there is a semantic problem. What are we talking about? An equation gives the meaning of those, gives the semantic of those primitives. Also, when you want to define the semantic with equation, then you should rather have a small number of primitives, otherwise you have plenty of equation. So it's safer. Also, well, there are these other things. Especially as soon as you have equation, then you can run tests or proofs against these. I didn't do that, and perhaps the reason is that this is all in monads, and perhaps next year John will explain to us how to make quick check under the monad. Okay. So for instance, the type of question I am asking myself on mutable variables I am using, equality is different. And as we shall see, I need to hide equality on mutable variables, because the equation I'm interested in won't be satisfied if equality is available. So what it is good or bad for, well, this is not that clear. And for very good reason, I guess, eventually decided after, in some version of concurrent Haskell, to define equality on mutable variable, but these reasons could be motivated by more precise arguments. So an overview of my talk. I will precisely describe what is asynchronous concurrency built on top of a monad. This yields the notion of monad references. This is a new name I used because there were already plenty of names describing what a promises is, and so they were all overloaded, so better to start with a fresh name. It makes some sense, because a monad reference will be a reference to a running monad action. Then I will explain what is a monad stream and how efficient it is, how nice it is. It opens plenty of interesting, rather theoretical questions as well. And last, I will explain how monad stream plus monad reference eventually yields concurrent monad streams, which is what I was interested in. Okay, so monad reference. What is a monad reference? So first, what is a monad? Let's recall what is a monad. So a monad is a type function equipped with two operators or two primitives, return, that lift a value into a monad action that returns that value, and a bind that allows to combine a monad action that returns a value and the function that waits for that value to create another monad action. There are three laws that are there that essentially says that in the this is actually they essentially say that somewhere there is a nicely defined category. What is important is that to do monad programming, so you are using return and bind, and fortunately, there is an alternative syntax that is sort of a lot more readable. In Haskell, there is this do syntax that can essentially be read as execute M, take the result produced by M, and then apply F on X. And this is equivalent to the bind. And since last March, which is quite a revolution, so sometimes people are thinking that Haskell, well, this is a cool language, but they are completely obsessed by monad and go to hell. Actually, in OCaml, there is such a syntax now in core OCaml for monad programming, and this is very cool, which means that even in OCaml you can do monad programming. And why monad programming is cool? Because monad programming looks like imperative programming, and actually that's quite the right intuition. And it's just a matter of changing the semantic of the comma here. And eventually you can have a program, and the question is not how to change, or a specification written of that form, and the question is not how to write a program out of that specification, but instead what monad should be defined so that your specification will be a correct program. So a monad reference is then, so there is a class type defining monad reference based on monad. It's essentially a type constructor that defines monad reference over a type A, and then two functions, fork, that launch asynchronously a monad action and returns immediately a reference to that monad action, and read, that take a reference to a monad action and eventually and return immediately an action that, when executed, will value that have been computed by the referenced action. So this looks like concurrency, but it's only asynchronous concurrency, so it's very safe. No possible deadlock with this. And there is a default implementation here. So a monad reference will essentially be a mutable variable because this is something that you can put a value in. And as soon as the value is in a mutable variable, then read action on that mutable variable will be executed and will return value. So essentially, nothing difficult, but the fact that I don't want equality to be defined on monad references. Okay. So what laws should be satisfied by these monad references? And I come first with a series of 3 laws. The first one essentially gives the semantic of asynchronous concurrency. It says that if you fork an action and right afterward you read the reference that has been produced by that action, then this is equivalent to with executing that action, side effect included. The second one, the 2 others, they are sort of a bit technical. You can meditate about their meaning. Altogether, they ensure that combining this reference type constructor with the monad constructor you start from, then you have a functor. The fork function yields a natural and one-to-one transformation from the monad functor to that combined functor. There is also sort of a reverse. Equality hold on one side, and you have only equality on the other side, which essentially means that whatever you can do in your monad, you can do with monad references. And the other way around is not true, because with monad references, you can write sort of more programs. There are more detail in the paper. I don't want to spend too much time on this. The problem is that with only these 3 laws, then there is a candidate for asynchronous functor. You essentially do nothing. And this is not concurrency. The fork doesn't execute the action, but just returns the action, etc. So there is a need to add some more rules that hopefully enforces monad reference instances to be truly concurrent. And I eventually come up with 3 rules that are a bit difficult to read, but essentially they say that reads are idempotent. So if you do twice the same read, it's just equivalent as doing the only once a read. Why so? Because one read may eventually wait a bit. This is a side effect. But as soon as it has waited time, the value you is available, so you can make a right afterward, and this would be equivalent to making a single read. Read are non-destructive values. As soon as a a value is available through its reference. You can do as many reads as you want. You don't destroy the available value. The two others are sort of classical concurrency rule. Forks commute, which sort of implies that forks are instantaneous. So their side effect as the order you make two forks doesn't change the related side effects. And reads commutes essentially for the same reason. So in the, actually this is what I just described. In the paper, for each of these new axioms, I have an instance that is correct with respect to the first three rules, and that violate exactly that rule. So it sort of shows what kind of bad behaviors are ruled out by these rules. And this this default instance satisfy all the rules. Is that known in concurrency? Well, if ever you can tell me, well, this has already been written. You're very welcome to tell that to me. Monad stream. So this very interesting, this very nice structure, monad stream, this is essentially, so a monad stream is essentially an action, a monad action, that you can execute, and either it returns nothing, telling you that the stream is over, or it returns a value, and the monad stream to execute for the continuation of that stream. So it sounds like programming by continuation, but sort of put into data structure. An example of monad stream is what I call the standard input stream, which is defined like this. You check whether the standard input is over or not. If it is, then you stop the stream. Otherwise, you get the next character, get char, and you return that character, and again the same stream. And what is interesting here is that we should, to some extent, using getChar, this is a bit a dangerous function, because if you use getChar in two concurrent processes, then you have the feeling that you are using the same function, but actually the result is not. So here it's clear that if you only use the standard input stream, then it sort of explicitly say that inputs will be gotten one after the other. So this is known. These streams and variants are used in Haskell libraries, especially conduit, but also channels in the concurrent the concurrent library. A simple function over those streams that shows that streams forms a functor. So the map of function M over the element of a stream, how do I do that? I execute the action of that stream, two possible cases. Either the stream is going on, so I got a value and a continuation of that stream, then I return the modified value, and then the recursive call on the continuation of that stream. Or the stream is over, and I return nothing. This shows that when you are using stream, that a monad stream can be used either as an input or as an output. As an input in this code, the outputs, the input here, the input aspect is here. You execute an action to get a value. And as an output, the output aspect is here. You create an action. And so with monad streams, you have a single encoded for both input and output. Also, what is quite interesting is that you can sort of both push and pull semantics. So if I want to print a stream, is it a push or a pull? It depends. If the stream is non-blocking, then it will be printed as fast as you can read it. So this will be a pull. You are pulling the value out of the stream. But if the stream is made of blocking action, like the standard input stream, then you can try to pull it as fast as possible. You won't go faster than the action executed. So it will be sort of a push semantic. It's because you will push value into the input stream that your program will execute. So combining these two things together, well, there is a bit of a miracle, is that there is this stream data type constructor that is parameterized by a type function. So far I used a monad as a parameter here, M. But instead of M, I can put the type constructor, which are the monadic reference on that monad, as soon as I do have monadic reference on that monad. And as soon as I have these things, then the reference of a monad stream will be a stream of monad reference. And this goes fairly well. Here is the code for the fork. And here is the code for the read. And I have that basic rule that tells me that if I fork a resulting reference to that stream I read, then this is equivalent to just returning that stream. Well, it's embedded in my monad, so there is a need to put the return around. Okay, if you read carefully this code, so how do you fork a stream? You fork that function, which is eval and fork the stream. And eval and fork, what does it do? It executes the action. Either the action is the value you get is nothing, you do nothing, or it's a value, then you fork the continuation of that stream and you return the value and the promise or the reference on that continuation. And you understand that in the case your stream is non-blocking, then this function will fork and fork and fork and fork, and running on the laptop, after a few minutes, it is using a few gigabytes of memory, of course. So it's not, we should distinguish blocking stream and non-blocking streams. So this is already cool. I have fork and read to do asynchronous concurrency, but this is not enough. And a function that is missing is a function I call par read, which take two reference and return the value produced by the fastest monad action that are referenced here. And with such a par read primitive, then I can define the function merge that take two monad stream and create the stream that results by merging those two monadic streams, sorting elements by availability time. And this is very interesting when you are doing control, because you may have, two sources of control, and you want to take into account the first control values that are arriving. I should finish, so I should skip over this. I already said what we have. So something that we don't have, and it would be very interesting, is that to add in the type system a distinction between blocking and non-blocking action, because that's sort of needed. And thank you very much. There are more in the paper that is available on the draft proceedings here. And all the code is on GitHub eventually, and I would be very happy if ever any one of you use it and complain, comments, etc. Thank you very much.